Great. Okay. Great.
And we don't hear recording in progress.
No, now it's starting.
I see, but somebody from Zoom. 1 second. Stella. Stella, вы нас...
Yes.
Все.
Да, я вас слышу, и слова были проговорены про запись.
Все отлично.
Recording in progress.
Okay, thank you everyone for coming to this physical seminar. It's my great pleasure to be introduced by Professor Kaboki. And in this seminar, we will discuss about the superconductivity with exciton mechanism. So the study of the exciton mechanism in the superconductivity is actually begun in last century 70s, and which is exact after the birth of the BCS theory. So though it was not a very newly born project, but nowadays still appeals many research for its large potential towards high DC superconductivity with the exciton mechanism. So in this seminar, in this seminar, at first I will briefly introduce the bone of the BCS, and then I will look at the exciton mechanism. I also show you something about the exciton proton mediated superconductivity, which is a leap forward towards the exciton mechanism. And so first we will talk about the BCS theory. So now we know that it is the phonon that plays a major role in the formation of Cooper pair, but it wasn't clear since 1950 when the isotope effect was discovered in the mercury. So you see that in this isotope effect, the critical temperature Tc, it is inversely proportional to the effective to the mass of the metal atom. And it means that the mass of the atom will have an impact on the critical temperature, and what is related to the atom mass is the phonon, because the lattice vibration frequency is directly related to the atom mass. And then people started to realize that the phonon can mediate an attractive interaction between the electrons, which should be repulsive. And in this period of time, Bardeen and Pines did much work on the scattering between the phonon and the electron. And 6 years later, Cooper pointed out that the momentum of two electrons should be opposite to form the bond electron pairs in the degenerate Fermi gas, which is now what we call the Cooper pair. So we can consider two electrons near the Fermi surface, which is scattered by the phonon. The requirement of the momentum conservation indicates that the momentum of these two electrons shall be exact opposite to reach the maximum possibility for scattering. But Cooper only explained this property of the single Cooper pair apparently. So superconductivity is a microscopic phenomenon, and only one Cooper pair cannot make the superconductivity happen. So in the next year, the BCS theory was born, and the large success of the BCS theory is that they gave the wave function for the Hamiltonian involving the electron-phonon interaction and the electron-electron scattering. So in the BCS wave function here, the particle number is not a conserved value. So it was strange at that time. But now we know that the superconducting phase transition is the second order phase transition, and with U1 gauge symmetry bracket. So this means that the system will choose a certain global phase. A certain global phase and the particle density is the conjugate pair with the phase. So which is exactly like the momentum and the space, the time and the energy. And when you have an exact phase, it will make the uncertainty of the density of the particle to be infinite. And that is, one can have an arbitrary number of Cooper pairs in this kind of system. And back at that time, the wave function is really a great discovery. So the spirit of the BCS theory is that they simplifies the electron-phonon interaction. So electron-phonon interaction itself shall be both momentum and energy dependent. But for the low frequency interaction, where the omega is approaching zero, this term, this propagator will be only -1. So will be -1. And then you can have a constant effective interaction between electron and electron, which is induced by the phonon. So it's attractive. And then BCS theory will give you the gap equation here. So the epsilon zero is exactly the gap energy. And the gap is exactly the minimal energy to overcome in order to make an excitation. So what can we get from this kind of gap equation? So by setting the temperature is hitting the beta to be zero, and when we will have the zero temperature superconducting gap, which is here, and also by setting the gap epsilon zero to be zero, and when we will have the critical temperature, which is here. And
should it be debate frequency?
the debate frequency for the phonon to be cut off here. And one can have the dispersion, which is parabolic, and also the gap you find here. Because there is a simplification in this kind of interaction, a more general form of the gap function shall be momentum dependent. So the success of the BCS theory is very large. However, the effective attraction interaction between the which is induced by the phonon will not be sufficiently enough to overcome the increasing of the thermal fluctuation especially when the temperature goes very high. Macmillan once pointed out that the critical temperature according to the BCS theory will not be no more than 40 Kelvin. This makes people to search for other options to increase the critical temperature. So even at the room temperature, superconductivity, and the exciton comes into people's side. So, sorry, the exciton comes to, yeah. No, okay. So yeah. Here we are. Exciton has many similarity with phonon. There are both bosons, and which means that the exciton may mediate the interaction between electrons like a phonon, and to make that form a Cooper pair. And
Да.
Ну хорошо, ладно, продолжаем.
Sorry, colleagues, because Windows decided to update itself immediately. 1 minute more and we continue. See. See. Yes. Ага, запись уже, да. Все. Dear colleagues in Zoom, do you see the screen?
Yes, I see.
Yes, it's healthy.
You see
And there is even
presentation.
And it is even better than previously because we do not see the nodes.
See. Okay, good. You can continue.
Thank you.
We stopped not probably, on the excitonic mechanism. It was, one second.
Yeah.
It was here. Yes, and probably next slide.
So yeah, thank you. So the early research on the exciton mechanism can be tracked back to last century 70s. And the pioneer is Ginsberg, was Ginsberg. Also, John Badin, Valito, and also many researchers have made much work on the exciton mechanism. So just like it was very popular at that time, just like nowadays people are crazy about the perovskite. And the general idea to have the exciton mechanism superconductivity is to place a very thin metal layer on a semiconductor surface. So in this model, the metal electron will penetrate from the metal to the semiconductor, where the exciton in the semiconductor will work like a glue to provide a attractive interaction between these electrons. And this is in the direct analog with the phonon mechanism on the superconductivity. So I will talk about some of my work on this exciton mechanism. So here you see that if we place a metal as the interface of the semiconductor, then there must be band-bending effect. And this band-bending effect will create this band-bending effect will certainly create the a potential where we can simply treat it as a linear potential. By solving this kind of quantum mechanics problem, we will see the energy level is quantized, and the wave function is exactly the every function, and every function with energy. Yeah.
So the functions of electron are all separately.
No, just for electron. So we propose that the electron is in the well potential, triangular linear potential. Yeah, and
is not it known that the just x product, the exponential, is an extreme variational, is extremely good approximation for this heterostructure, for this triangular potential, because even on the samples of field transistors, they publish the spread of this exponential. I mean, any function is an exact solution, but the problem is the potential is approximate itself. So
yeah,
why not to use
I see.
something simpler than the area function?
I see. There must be some more accurate potential profile to simulate the band-bending effect near the interface between metal and the semiconductor. But the linear potential is kind of is one way to simplify this problem.
Yeah, I know. So but that's exactly what I'm saying, that you already made an approximation of a linear potential.
Yes.
Yes, then your level of complexity is too high. Why to use area function if the function, which is x product e to the minus bx, is good enough approximation and much simpler function? So you already did a simplification. So the potential is already not exact. Why do more complicated function as well? That is a good approximation.
Yeah, because every function is a solution, exact solution to this.
Yes, but it's known that if you plot x e to the minus bx versus this area function, you will not see the distinction by a naked eye without a microscope. It's a very good approximation.
Misha, this is for the ground state, but here also excited states are important, at least one of them. So it's
okay. I understand. Thank you.
Okay. Thank you for the question. And then we consider two channels for the scattering in this problem. That is, the electron can be scattered from the energy level event to itself with the increasing of the kinetic energy. And also, we call this intraband transition. And there's also another type of transition is the interband transition. Interband transition happens when electrons jump from the energy level E1 to energy level E2, where the so this is the interband transition, and these two different scattering channel will provide us with a stepwise effective electron-electron interaction. So this is different from the BCS theory. So you see here is the background. This background is provided by the phonon, where the truncation energy is Debye energy. But for the interband transition energy, interband transition and the intraband transition, we have a different cutoff energy. So, for example, the intraband transition happens between happens when the electron only gains kinetic energy, and the energy cutoff is exactly the energy difference between the band, the second band and the first band. When yeah.
So,
Yeah.
what you calculate here, you calculate exciton electron scattering, right?
Yes.
So how you describe your excitons?
So
Do you account for some surface effects?
here.
So you give wave function. This is, you say, electron wave function, right?
Yes.
So what about exciton?
So here we consider the case as electron in the exciton is a heavy exciton. So the heavy hole. So the hole will not will remain here, as the exciton will be participate in the momentum transfer between these free electrons. This is what we treated in this in this case. I will show you some
You calculate this scattering matrix.
scattering matrix.
The one you show, the diagram, you calculate it correctly.
I calculated it. I will show you it later. So I'll calculate it with random fast approximation.
Excuse me, please. Can you show the previous slide? Okay. So the upper left picture, you see, you created a hole in the semiconductor nearby the metal, yes?
Yes.
But then another electron from the metal will immediately go to this hole and close it. Why not?
Actually, in this case, the semiconductor, the exciton in the semiconductor itself is a stable step. The free electron in this metal will not fill this hole, but be scattered with electron here.
Yes, but my question, is there a tunneling between the metal and the semiconductor? Do you account for tunneling between the metal and the semiconductor or not?
No.
No, okay. So the semiconductor exists, but there is no contact with metal. And you consider
with the metal. Yeah.
Not the metal. And is it important for you that that electron and hole are bound to create the exciton?
Yes. Yes. Here the electron and hole shall be bound.
But then you see there's such effect which is called sorry, I forgot the. Please, tushение. Tushение. What is the English for? Sorry for my deteriorated English. Could you please help me? What is the English word for tushение? тушить.
Proximity, touching.
Oh, you mean the proximity effect of the superconductor?
No, not proximity. I mean the following, that because you created an exciton or electron-hole pair, then due to the presence of the metal, this
not due to the presence of the metal. So this kind of binding effect, the exciton itself can be think as can be solid as
no. You see, but this exciton can immediately annihilate with giving its energy to electron of the metal. This is can immediately decay and quenching. This is okay. So this effect, quenching of excitons nearby the metal, was considered by Agranovich, Malshukov, some other people just near in the beginning of, or at the end of 70s, in the middle of 70s, in the middle, or in the beginning of the 70s. So excitons are not stable nearby the metal. They immediately decay to the metal.
Yes, but
so they immediately decay, transferring the energy. The energy is transferred to the metal because.
I can maybe comment on that because
yes.
Excitons, the temperature is finite. So excitons do not live infinitely, but there is always some population of excitons because of finite and even high temperatures. The energies, these exciton energies are much smaller than optical energies. These are basically excitons formed at closely spaced energy levels in this triangular well. So it is expected that the lifetime is sufficiently long, even so, of course, it is not infinite.
Lifetime with respect to which process?
Formation of the Cooper pair, so scattering with electrons.
No, not Cooper pairs, just ordinary electron-hole pairs in the metal. You see, you have an energy, you have a metal nearby. So the energy, you have a metal is a huge reservoir of potential electron-hole pairs. So the energy of the exciton can be transferred to the metal. It's a kind of a jet process.
Yes,
and this process is very fast.
You have two competing processes. One is exciton electron scattering that is governed by a long-range Coulomb potential. So you can scatter an electron which is far from you. And the other thing is this exciton non-radiative recombination due to tunneling of electrons from the free electron gas. Or
No. Just I mean the following, that electron and hole annihilate, and the long-range Coulomb potential transfers the energy of this annihilated exciton, transfers this energy to the metal and excites an electron-hole pair within the metal, or many electron-hole pairs. Just excitation of the metal. So in a much simple way, you can say that, okay, you have some dipole nearby the metal, and you have a metal which absorbs and the metal has absorption. So the energy of this dipole is immediately absorbed by the metal.
Temperature is not zero. You see, so when temperature is not zero, you can have excitations in any structure. So this is a low energy excitation in this heterostructure. And it exists, there is some concentration of such excitons just because the temperature is different from zero.
Okay, then in the metal you also have electron hole excitations corresponding to such energy. Okay.
Okay, thank you for the question. Yeah, so by proposing these different scattering channels, and we can have multi-step wise effective potential, and this can be solved iteratively solved by and finally we can produce the gap function based on this effective effective potential. And you see, because of the participation of the exciton, the effective interaction constant is actually higher than the electron than the pure phonon induced electron interaction, which means that the critical temperature can be higher in comparison with BCS theory. And then in one of
ask about these parameters delta 1, delta 2, and eta 1.
Yeah. So
are they expressed in the exciton wave function from the previous slide? Functions or electron
I will explain them in this way. So here we see that the cutoff energy. So cutoff energy is exactly the energy difference between the energy level. So for example, the delta one means the intraband transition. It means that when energy difference is between E2 minus E1, so this gap from the solution of the linear potential, and it means that the electron in this exciton can only have the intraband transition, which means the kinetic energy is increased, and in this case, so delta 1 is exactly the energy difference between E2 and E1, and then it's delta 2. So delta 2 is the energy similarly delta 2 will be the energy difference between the E2 and the E3. So although I did not draw E3 here,
there energy levels of what the metal semiconductor.
This energy level is calculated from this belongs to the electron in the exciton.
Excuse me, I would like to.
Electron scattering to exciton, electron from metal. Right?
Here we think about this case. So this exciton, we have a heavy hole. The hole would not directly participate in this kind of scattering. You can think it is stay as still, but the electron in the exciton will be scattered with the free electron in the metal to help the free electron in the metal to form a Cooper pair. So that is what we proposed in this case. So you see when the electron in the exciton be scattered to somewhere, for example there, and then it will scatter another electron in the metal and will recover to its ground state, for example E1 to the ground state, and then
so you just use word exciton, but you never deal with exciton, right? You calculate just electron collision.
Yeah. Here it seems to be so, but I will show the actually this is right closer to the case when we consider the electron exciton interaction into the system. I will show it to you later.
So probably, Panik, the right thing would be to refer to the works on the excitonic insulator on the surface layer, in this Schottky barrier layer in silicon-based heterostructures. There is a lot of works on that, and basically they study these kind of triangular potentials. What is important for us is that if you have an exciton, the electron sits in the empty subband. That is why it can be scattered to any k. within the subband. A hole potentially can also be scattered, but well, it may also give some contribution. I think then the approximations start, and why not to consider just electron scattering for simplicity?
Yes, who can participate? That is true. It depends
Okay.
on. Okay.
May I ask more?
Yeah.
You see, you have suppose you have electron and a hole in the semiconductor. So they are restricted. Their motion is restricted in that direction, but they can move in the parallel direction. So my question: in the parallel direction, do you imply that electron and hole really form the bound state, the exciton? So do you believe that in the parallel direction the electron and the hole are bound, or they move independently? So do you really mean an exciton, or you simply mean some electron-hole pair in the semiconductor?
We can.
So I think the question can be reformulated this way. When you calculate this scattering matrix element, you need to put wave function there. So is this wave function the in-plane part? Is it exciton wave function of bound electron hole pair, or just the electron wave function as a single part?
Yes, I see your concern. So now what we consider, what we calculate here is just the electron wave function. But okay, I will directly show you the result. So when we consider the electron exciton interaction into this case. So basically we can write down the Hamiltonian like this, where the first two term is dispersion of electron and exciton, and the latter two term, the third term, it is screening effect of the electron. No screening. It is a Coulombic interaction between the electron, and the last term it is interaction between the electron and the exciton. So here the Vx is potential for the for the electron and the exciton, and you see these parameters can be tuned to balance the participation of the electron and hole. So we can propose that the hole maybe beta h, it can be infinite. It means that the whole mass is much larger than the electron mass, indicating that the electron can be scattered more easier than hole in this case. But it doesn't matter. Okay, so after some treatment, we can we can simplify this four operator term into three operator term by the Madeleine transformation. We can see where we assume the most excitons are staying in their ground state, and then the annihilation operator and the creation operator will just create square root of n or square root n plus 1 particles. And we can also assume that the particles of the exciton is very large. The number is very large, and it means that the square root n is approximately the square root n plus 1, and then we can have this kind of three operator form to simplify as a result of simplification, and then
this potential you're showing, I think this is theoretical. Alexei, right, with Ivan Shulov?
Yes, it's
there was, so this was calculated. There was some barrier, right? L is the distance between semiconducting and the metal.
Yes.
So here you need to put it 0 or
no. The error should be 0 point something nanometer. So in the level, in order of angstrom. So this is the error. Error is actually the mean the mean distance between the free electron in the metal and the exciton in the semiconductor.
So it depends on the thickness of the layer of aluminum,
Yes,
which
thickness.
maybe we could have shown the experimental results that inspired this work, where they changed the thickness of the layer of aluminum, and they studied the dependence of the critical temperature for superconductivity on the width of this layer.
Yes. Yes. So then we can use this propagator of the exciton to calculate the effective interaction induced the effective electron interaction induced by the exciton, so which is just as a Vx square and product the propagator of the exciton, right? And then with random phase approximation, we can where chi0 is the susceptibility, and then we can finally have the result. I will show you what I will show you in that here. So with RPA, you can have the effective electron interaction, which is exactly like what we saw the Ellsberg equation will have, and this is stepwise potential, which is obtained by the previous model, where the electron only interacts scatters with the electron in the exciton. You will see that the actually the step potential is a good estimation to the effective electron interaction. And also the exciton mechanism may explain the superconductivity of the aluminum thin film on the silicon substrate. So these red dots are actually experimental results from a published paper, and we made such comparison to this. This is what we found for the exciton mediated superconductivity. Okay, next I will introduce the exciton proton mediated superconductivity as a one step beyond the exciton mechanism.
Dear Junhui, for that first part, I believe it is also very important to compare the dependence on the width, the critical temperature, the gap dependence of the width of aluminum.
I did not put it, but
qualitatively it should be possible to explain it with this model.
So okay, yeah. So yes, exactly. So especially when
Excuse me, the figures were experimental figures or theoretical figures?
All points are experimental.
Red points are from experiment, and these figures are produced by our model and also the RPA calculation.
So gap energy dependence on the temperature, yes?
This is a gap function, yes. Energy dependence, gap energy dependence.
And what about the pure aluminum?
Pure aluminum, it will be
pure aluminum film without
it's
without
about
the semiconductor.
2.4 Kelvin. For pure aluminum metal, it will be about 2.4, whereas there's only phonon contribution. But this is for the aluminum thin film. So the critical temperature is about 3.5 Kelvin.
Okay, once again, ask. So what about the depth of these two steps? Were they calculated from the wave functions of electrons and holes, or how?
Yes, they are calculated from the previous model. So I will show you. This is it is similar to this. Yeah, this is similar to this. To the physical picture which I explained before.
Is there an expression for this? Eta 1 and eta 2?
Eta 1 and eta 2.
Maybe
There's expression for it, but I did not put on it here. There's expression why.
But actually, it is based on this potential Vx of Q. You see where there is electron term and hole term, and hole term is neglected, but the electron term, it depends on the concentration of excitons, on the Bohr radius, on the masses, and the distance, average distance between the free electron layer and exciton layer, and also a dipole moment. I think G is the dipole moment of exciton. So all these parameters are accounted.
Yes, for the exciton polariton, it seems to be more interesting than the exciton itself, as you can modulate the polariton in the system by the light pumping in to increase the not increase, to control the density, particle density, and
Excuse me, you expected to obtain high TC, but you saw 3 point something.
Yes, I am supposed actually it is already what we call high TC. It depends on the parameter or the experiment setup. So for BCS, we compared it with BCS. So for BCS, we can only get 2.4 Kelvin, which is exact the phonon contribution. But if you consider there's exciton participated in this case, and then the critical temperature is increased. Yes, exactly. So
This is the strong argument that the exciton mechanism is actually playing the role. So principle.
But the other argument is this width dependence, because when I think in the limit of one monolayer of aluminum, it is even high. It is more than 4. If I remember the term. Proximity, yes. The closer they are, excitons and electrons, the higher is critical temperature. So the stronger is the impact of the excitonic mechanism.
That's true. And for the exciton polariton part, one can do the Bogoliubov to diagonalize the to diagonalize this polariton for operators, and I show you the result. So first is effective potential, which is very important, which is important for all the superconducting cases. So here you show that it is also attractive in the low frequency, but repulsive when the energy exceeds the energy of the Bogolov, which is a quasi-particle here. And in our case, this is exciton, but here is the Bogolov. And but one major difference is that you see there's a jump of this potential here, but for exciton, it is something like there's no such kind of jump here. It's just increase and then decrease. The major thing is that in the exciton polariton mediated superconductivity that also shows the possibility to reach the room temperature at about 7 times 10 to the 11 per centimeter density of the polariton, which can be achieved in realistic cases. This is not a high density for polaritons, and which shows possibility to reach the room temperature if the in reality. Yeah. Finally, I will summarize this with a paragraph from the literature. So the exciton mechanism itself, it would be a great achievement, and for exciton are well controllable with modern experimental techniques, and also the potential to achieve the high critical temperature. So Okay, so although the success cannot be predicted with any certainty, so but it has a solid theoretical support and worth more attention and effort. Thank you very much. That's all.
Yeah. So, any questions from online audience?
Yeah.
Some questions in the talk and here. Yes, Anton.
What is the mystery between this huge leap from 4 Kelvin to room temperatures when replacing excitons with bosons? Which parameter drastically changes the prediction?
Many, exactly. So the first, so in this setup, the spacing between the quantum value and the 2 DEG is a tunable parameter, and also the exciton density is a tunable parameter. For in our case, for example, the 4 Kelvin like this, the density of the density of the exciton it is only 10 to the 9 or 10 per centimeter square. But here you see that the density is very high. It can be 10 to 11 or 10 to 12, like this is order. So the density of the density of the quasi-particle is actually also another very important parameter here. And also the dipole length, the length of the exciton dipole, which I will show you in the electron exciton interaction term here. It's very important. Hidden and also the Bohr radius of the exciton. These are the main major parameters for the electron exciton interaction.
But I would also add that for polarions, you can have Bose-Einstein condensation at room temperature. And for excitons, you cannot. And here, clearly, if you have a bosonic condensate, then the density of this condensate plays a role. If you have no condensate, it is some effective density which is much lower than plays role in the interaction.
But which density is actually involved in the expression for the critical temperature? Is it the density of bosons or the density of
the condensate itself? Or bosons, they are just virtual excitations. And excitonic is the density of excitons in the condensate or some effective density that here you see. If there is no condensate, you would have a lower density than if you would have a condensate. How much lower it is a question, but somehow low.
May I ask about the experimental configuration with excitons? You see, my question is, you have such a complicated system, and you suppose that there are excitons in this silicon, yes? Silicon layer. My question, is it possible to use optics, absorption, just to measure optical absorption when light passes this system from the silicon side in order to find the evidence of the existence of excitons?
Yes.
Is it possible?
I agree. So in experiment, if you want to make sure that the exciton participate in such kind of superconductivity, it is a good idea to control the density of the exciton, for example, by the light, and to see if there is a change in the critical temperature to build up the relationship between the exciton and the superconductivity. Yeah, I agree.
Okay, thank you.
Thank you.
More questions? Okay, if not, then we have our traditional gift
Thank you very
because of a pin. You can put it on your jacket
Great.
as a speaker of this seminar and also now the member of the Abrikosov Center.
Great. Thank you very much.
So the next week, do we know who is the speaker?
Probably me.
You are the speaker.
Yes, probably. I'm not sure. It depends on the decision of Boba, but he asked me to have a talk on the next week.
Great. Okay, good.
Андрей, что тут надо делать?
Окей, спасибо. Всего доброго.
Давай.
Ну,
Запись.
я понял, что вы правы.
Стоп, да?
Значит, на эту